All right, Chem students, today we're going to start our stoichiometry unit. You'll need your stoichiometry notes, something to write with, and a periodic table. Now, stoichiometry is the calculation of quantities in a chemical reaction. You have to have a balanced chemical equation in order to do stoichiometry calculations, and that's why we covered that first. You will use a given amount of one substance in a chemical reaction to calculate an amount of another substance in that same reaction. If the equation is balanced, this will work. Okay, a quick review of mole conversions. You will need to use these conversions for many of the stoichiometry calculations. 1 mole equals 6.02 times 10 to the 23rd particles. 1 mole equals x grams, where x is molar mass. For example, 1 mole of CO2 is going to be 44.009 grams. We get this from our periodic table. And 1 mole equals 22.4 liters. That's for gases at STP. So if you see volume or liters, this is the one you're going to need. Now let's do an example for practice. How many moles are in 5.0 times 10 to the 25th molecules of carbon dioxide? So here's our starting point, 5.0 times 10 to the 25th molecules of carbon dioxide. That's what they gave us. Now, we know we're given molecules and they're asking for moles, so we're going to need a mole-to-molecule conversion factor. Molecules is where we started, so molecules needs to be on the bottom here. And when we do the math, multiply across the top, divide by the bottom, we will get 83 moles of carbon dioxide. I kept 2 sig figs because I started with 2 sig figs. Now, try on your own. What is the mass in grams of 0.250 moles of carbon dioxide? You should have gotten this. We started with 0.250 moles of carbon dioxide. So we're going from moles to mass, so we need the mole to mass conversion factor. 1 mole will be on bottom. Carbon dioxide is 44.009 grams in 1 mole. We multiply those across, we get 11.0 grams carbon dioxide for our answer. Last example for you to try. How many moles of carbon dioxide gas are in 100 liters at STP? So take a minute to do that one. Okay, let's see how you did. We start with 100 liters. That's what they gave us. We're going from liters to moles, so we need the liters to mole conversion factor. There are 22.4 liters in 1 mole. 100 times 1 divided by 22.4 gives us this as our answer. So we have an equation up here that's been balanced, and this can be interpreted as follows. If we take 2 atoms of solid iron and react them with 3 molecules of chlorine, we will produce 2 formula units of iron chloride. Now, we can interpret those coefficients that we use to balance this equation in another way that's actually more useful, moles. We can have 2 moles of solid iron reacting with 3 moles of chlorine gas to produce 2 moles of solid iron chloride. It's like we multiplied the whole equation by 6.02 times 10 to the 23rd. Now, it is much easier to use moles in lab than it is individual atoms of a substance, so that's why we're always going to use moles. Now, a mole ratio can be written to compare any 2 substances in a reaction. Now, if we have this example here, we have boron trifluoride reacting with H2O, and it's going to give us diboron trioxide and hydrofluoric acid. So first, let's balance it. So that's what we would need to balance it. 2 boron trifluorides plus 3 H2Os will react to form and produce 1 diboron trioxide and 6 hydrofluoric acids. Now, the ratio of boron trifluoride to H2O is 2 to 3. In stoichiometry calculations, this ratio will always take the form of 2 moles of boron trifluoride over 3 moles of H2O, or the opposite, 3 moles of H2O over 2 moles of boron trifluoride. Both of these are correct, and we would use them in the calculation depending on where we started. Now we're going to practice using the balanced equation above. Write the mole ratios for each. So boron trifluoride to diboron trioxide, we would have 2 moles of boron trifluoride. The 2 is up here, and that will react to form 1 mole of diboron trioxide, which is over here. So we're just looking up the numbers in front of each substance in the equation. And the reverse of this would be 1 mole of diboron trioxide over 2 moles of boron trifluoride. Now for the next one, we have 3 moles of H2O over 6 moles of hydrofluoric acid, and the other one would be 6 moles over 3 moles. Now the last one, diboron trioxide to hydrofluoric acid. We have 1 mole of diboron trioxide on top of 6 moles of hydrofluoric acid, or we can reverse that. These are equal to each other. Okay, that's it for today's lesson. We'll see you on the next video.